Okay, next topic we have is partial derivatives and critical points. How are they related? So we're going to have a definition for critical points in R3. And then the other thing we're going to do is figure out what something like this means. When we get a partial and evaluate it at a point for an R3 surface and we get some number, what does that mean? We have one meaning so far, which was the marginal interpretation of the partial derivative. A 1 unit increase in x, because that's the variable, y held constant, because that's how you computed the partial, results in about this much change in the z-value. We're going to now add a visual and geometric interpretation of what that means, and then relate those ideas to critical points in R3. Okay, so let's start with the visual aid. So we're around a page, there's a page in your journal, Geometric Interpretation of the Partial Derivative. This will be a good one to do this activity at home. I'm going to do part of it here for you now. So it says, get a hemisphere. So maybe an orange or an upended serial bowl. So I'm going to use this upended serial bowl. We're going to imagine that this is actually a perfect hemisphere and it doesn't have this plateau here. We're going to then sit that on our XY plane. So I'm using the back of my journal. I'm going to put an XY plane there. And then I'm going to put my serial bowl on there. And we're going to go to a point on the surface. And it's okay to write on this because it's Expo pen. So I'm going to put a point on the side of my surface. And the way I've oriented here, it looks like that is the point. Let's imagine this is a hemisphere. This hemisphere. Talked about this a couple times. This would be a hemisphere with a radius of 3. That would be the top hemisphere. And we're in the top part of the XY. Z is here, so we're in the upper hemisphere. And so it looks like I'm pretty close to the radius of 3, but maybe I'm really closer, like 2. So there's 3 points on my axis. And then it looks like I'm about 1 along the Y. So the point that I've chosen, it looks like that is about at the point on mine, the point X is 2, Y is 1. Okay, so I'm there on the hemisphere. And then we're going to wonder, what does this mean? F sub x at 2, 1. And we can actually compute it for this hemisphere. So let's maybe go ahead and practice that so we can practice some partials. So this is my f of x, y. Oftentimes you take the square root and turn it into its exponent form. So let's go ahead and do that. That's going to make it easier to take the derivative. I want the partial with respect to x times the power. Take what's in parentheses down a power. And then take the derivative of what's inside with respect to x. So the derivative of what's inside the parentheses with respect to x is minus 2x. So the 2's cancel out, and so I'll have a minus x. If I want to clean it up, over the square root of 9 minus x squared minus y squared. Okay, so that's my partial with respect to x for any xy, but I want to do it for 2, 1. So let's just plug that in and see what kind of number we do get. So when x is 2, I'll have 9 minus 2 in the numerator, and then I'll have, let's see, 9 minus 4 minus 1. So 9 minus 5, oh, that's nice. So square root of 4 is 2, so minus 1. Oh, that worked out really well. That rarely happens when you make something up. Okay, partial with respect to x at the point 2, 1 on this upper hemispherical surface is minus 1. We have the marginal interpretation, which says when x increases from 2 to 3, y held constant, z goes down about 1 unit. Let's see what that means in the visual geometric interpretation. So back on our surface, in our desktop coordinate system, so I'm at the point 2, 1, so 2 along the x, 1 along y, up to the surface, and that is like square root of, oh, it's 2 again. Okay, so I'm up here at this point. And what we want to do is imagine what happens here. This turns out this is going to be a slope, this minus 1, just like it was in R2 when you took a derivative. back in R2. Y was a function of x. Say it was x squared. F prime of x was 2x. You evaluated a point like 1, you got 2. That was the slope of the tangent line, right? This is going to be a slope of a tangent line inside a particular plane. And so let's visualize what that means. Remember, this is when y equals 1 is what kind of plane? Is it horizontal? No, it's a vertical plane. And that's because y is held constant, right? It can't move outside that plane. On the other hand, x can vary, but it can only vary inside this plane. So let's go ahead and graph the y equals 2 plane in this desktop coordinate system. Sorry, the y equals 1 plane in our desktop coordinate system. So here's 1. It would be here, and then we orient it to the right side. So it's a vertical plane through y equals 1. Now let's do that with the surface, right? So here's my surface. Now I'm going to graph the y equals 1 plane. I need more hands. The y equals 1 plane is this vertical plane that comes down over top of the surface, and then you can see that the point, it goes through the point on the surface, on this upper hemisphere. And now, how many, I'm going to maybe see if I can angle the camera a little bit differently here so I can use this table. How many different tangent lines live in that plane, go through that point on the surface? Let's see if we can get this angle. Yeah. All right, let's see if we can get that up. All right, so there's the point on the surface. This is the y equals 1 vertical plane. How many different tangent lines are of the infinitely many in the tangent plane at the point of tangency? How many of those infinitely many tangent lines live in the y equals 1 plane? 1 and only 1. So let me orient this a little bit different so maybe you can see there. All right, so my pen, right, this pencil is darker, it's a little bit better to see, is the only tangent line of the infinitely many that live in the tangent plane that goes through the y equals 1 plane. Its slope, the slope of that line, is -1 in this example. That's exactly what this partial means. So the visual interpretation, it's important that you can visualize that and then verbalize it. This is the slope of the tangent line through the point of tangency, which in this case is the point 2, 1. That lives in the y equals 1 vertical plane. Right. Again, there's infinitely many tangent lines through the point of tangency that create a tangent plane, but there's one and only one that lives in the restricted vertical plane. You're restricted by the fact that you computed this partial derivative where you held y constant. And this shows that the slope is negative, and therefore we'd have a decrease in z if you were to increase in x. Which, again, we kind of saw that. It makes sense from our hemisphere here that if we were to move in the positive x direction, moving out this way, we'd move down the surface, and so we would decrease in the z value. Right, so what do you think this means? F sub y at 2, 1. We could go ahead and get another partial. We could calculate it, and let's put a number there. It's going to equal some number. Write the verbal statement. Pause the video. Try to write an analogous verbal statement for what you think the partial with respect to y at a particular point is, and then try to visualize that. Okay, you come back from trying that yourself. So the partial with respect to y at this point, again, let's just make up a number. For now, we'll do the computations in a bit with some tech tools and another font. Let's just say it was 7. What would that mean then? That would mean, verbally, that we could state that 7 is the slope of the tangent line through the point of tangency, which is still 2, 1. That lives in which plane though? When you do a partial with respect to y, you treat y like the variable, and you treat x like a constant. That's how you computed the partial. So it would be the one that lives in the x equals 2 plane. So back to our visual aid. Again, do this at home. This is a really good one. You all have the equipment to do this. Just grab a cereal bowl, mark it with a point. And now we're going to be in the x equals 2 plane, also a vertical plane, but it's going to move like x. Instead of this sort of y equals plane, we're going to have the perpendicular plane, which is at x equals 2. We're still at the point on the surface, right there, in this plane, and the tangent line that is touching, it goes through the tangent point and it lives in this plane. And that would have whatever slope this partial gave. Okay. So that is our idea for what the geometric and physical interpretation of a partial with respect to x and a partial with respect to y is. And now we're going to relate those ideas to critical points. So what does it mean to be a critical point? Back here in R2, we said you were a critical point if what happened? If the first derivative was equal to 0, which is another way of saying that it was a point on the function where you had a horizontal tangent line, right? And so we're going to, instead of having horizontal tangent lines, what would you take a guess? We'll have horizontal tangent planes, right? So a critical point is a place where your surface, f of xy, has a horizontal tangent plane. And how do you think we're going to find those? Instead of setting your first derivative to 0, what do you think we're going to set to 0? Remember, so much of Calc 3 comes from ideas from Calculus 1 and 2. So we're going to extend ideas that we already know and figure out what it means to be a critical point. Another way of saying it, it's a place where you have horizontal tangent planes, but it's also a place where f sub x at xy equals 0 and f sub y at xy equals 0. So instead of your first derivative equals 0, your first partials equal 0. Both of them have to be 0. But I should also be a little more specific. It's a point xy where that happens. So we're not just finding an x value like we did here. Because we're in higher dimensional space, we need to find a point which now represents an x and a y value that satisfies both first partials equal to 0. So we're going to go ahead and crank away on some calculations and practice finding critical points. But let's, before we do that, pause for a moment and think geometrically, why would this make sense? Why would setting both first partials to 0 be a place where I have a horizontal tangent plane? Well, again, if I'm on a surface at a point on that surface, and I set my partial with respect to x, well, that's going to move, partial with respect to x is going to be restricted to be in a vertical plane, a y equals, wherever you're at. So there's some y equals plane coming down here, and then there's a tangent line, and it has to have a 0 slope. So we have a horizontal tangent line when we're restricted to be in the y equals constant plane. And then we go and get the other partial. The partial with respect to y means we're restricted to be in a perpendicular plane. And we have a tangent line there. And that also has a slope of 0. So the example that I had, this point here, maybe that one was horizontal, but this one isn't. So the tangent plane is a tilted plane. On the other hand, if I'm up at the very top, I go ahead and get a tangent line in the f sub x, which means y equals a constant plane. And then I get the other one, which is perpendicular. And that also has a slope of 0. The only way those two tangent lines that have slopes that are in restrictive planes that are perpendicular, they both have 0 slope, would be that I would then create a horizontal plane, right? Sweeps out a plane. Okay, so that's why it makes sense to set both first partials to 0. That's why you're getting a horizontal plane. Well, let's go ahead and practice with one that we want to go ahead and compute the critical points for. We'll get rid of our visual aids here. And let's compute the critical points for this function. F of xy equals x cubed minus 6x plus xy minus y squared. Okay, so I tried to pick ones that aren't shown in your journal, so then you have plenty of other examples to go through as you read your journal. Find the critical points for this function. So the definition is visually, you could go to Calplot 3D, plot this, and then just ride that little blue point, run around the surface until you can see if it looks like a horizontal tangent plane. But we can also do it having no idea what the surface looks like, just using calculus and algebra by taking our first partials. So we'll get those and we'll set them to 0. Just like you would have in R2, it's just extending ideas. So f sub x is going to be 3x squared minus 6 plus y. F sub y is going to be x minus 2y equals 0. Okay, now what you're left with, so what's in the box here, is what's called a system of equations. You've seen these before when you tried to find points of intersection back in R2. You've seen them when you try to find points of intersection of lines. So we have 2 equations and 2 unknowns. And so we can solve this. And there's several strategies. You probably remember things from back in high school that you might have learned. One of the techniques is that you see if you can solve for one variable in terms of the other. And that's really easy to do in the second equation. So the second equation tells us that x is 2y. And so that represents, they mean the exact same thing, these 2 things here. So I can take that and plug it into the first equation, which says whenever I see an x, I can actually put a 2y. So we're going to take this and push it into here. And then what I'm left with is just one equation and one unknown. And that equation looks like this. So I've taken the second equation, I've represented it in an alternative way, and I've pushed that representation into the first equation. So really I've subsumed 2 equations into one, which makes my job easier because I'm good at solving one equation, one unknown, or better at that, I should say. And so now we have something that's simpler. And what is this? It's not a linear equation, but it is a quadratic equation, which is sort of the next best thing. So we can solve that. So we'll have, let's simplify a little bit first. So we'll have, what, 412y squared plus y minus 6 equals 0. And if we're lucky, that factors. If we're not, we have to use the quadratic formula, and we're going to find a value for y. So let's go ahead and do that for a minute. Let's see, can we factor this? It looks like we're getting close, and I just have to get the signs right, so we might have a chance. We need a positive and a minus. Does that do it? 12y squared plus y minus 6. Yeah, nice. Okay. So we get 2 values for y. Set each factor to 0. That's the rule of 0. The only way 2 things can multiply and be 0 is if at least one of them is 0. So we have 2 simpler equations, which now these are linear, easy to solve. So we get y equals what? 2/3, and y equals minus 3/4. Okay, so is 2/3 a critical point? Is negative 3/4 a critical point? Go back and remember our definition. A critical point in R3 has to have an x value and a y value. And those two, that point, that the x value and the y value, have to solve both first partials. Well, by design, we know this y solves the partials. That was by design. That's how we massaged these equations and got this one solution. So let's see, how do we get, if there is a partner, how do we get it for y equals 2/3? It's right here in this solved equation. So this says, if I know y, I'll just divide by 2, I'll get my x. So y is x over 2. Or sorry, we already had it solved. X was 2y. Didn't need to do that extra work. So if I have a y, I just multiply by 2 and I get an x value. 4/3 and negative 6 3/2, I guess. Now, is each one of these, can I write it like this? Like this is a CP. Usually we write it in our parentheses, in our point notation. And another CP at -3/2, -3/4. Is that a CP now? Let's take the first one. If it's a CP, it has to be a point, an x and a y value, and it has to be that I take that and plug into the partials. So it has to be that f sub x at 4/3, 2/3 equals, I plug in 0, and f sub y at 4/3, 2/3, when I plug in, has to give me 0. So let's see if that's the case. So I plug into f sub x. 3 times 4/3 squared, so that'd be 16/9 minus 6 plus y is 2/3. So we need to do some arithmetic and check, does that equal 0? Let's see. So 18/3 is 6, minus 6 is 0, check. And then we check the other one. It has to be, again, both of these have to be true, and, right? So I don't know where it's an and. So f sub y at 4/3 is 4/3 minus 2 times 2/3. Easier one to check, yes. So this is definitely a CP. And again, it has to be by design, but that's just a way to check. And this one also is a CP. And that would mean that these are places where you have horizontal tangent planes. So you could check, this would be a good thing to pause the video, go to CalcPlot3D, put your function in, ride the tangent plane until you get to the point 4/3, 2/3, or close to that, or enter it in, and go ahead and see that you have a horizontal tangent plane there, which would mean the equation of the tangent plane is what? It's a good thing to check. If you have a horizontal plane, what does the equation have to be? Any horizontal plane is a z equals. So it should just be the height of the function at that point, right? So it should just be f of 4/3, 2/3 should be the tangent plane. It makes the equation from the tangent plane equation much easier to solve. Right, just real quick, make sure you get that point. Right, if you're a critical point, this is 0. If A and B is a critical point, that's 0. That whole thing goes away. This is 0. That goes away. You're just at the point. Z equals some number, right? That's your equation for the tangent plane. And check that in CalcPlot3D. Look up at the green bar on the top, and it should show you that that is the case. Oh yeah, one more thing I want to show you. So we showed you how to visualize CalcPlot3D, visualizing the tangent plane, but let me just show you one other tech tool. Okay, so CalcPlot3D, might as well just go ahead and do that while we're here. What was our equation? X cubed minus 6x plus xy minus y squared. Yeah. Go ahead and reset because it got confused about, I broke it with that other line. Not a bit. Oh, let's change this to like -5. Okay, so then we can see that this surface, whoa, it's a pretty bizarre surface, huh? There we go. Okay, and then you could go ahead and do this, show the tangent plane at a particular point. Let's pick a point we can enter in. What was ours? We said the critical point was at positive 4/3 for x and positive 2/3 for y. Yeah, and so there it is. You can see that little tangent plane transparency and show the tangent plane in the green bar. It's an approximation. It's the software that's using. It's really 0x, 0y, and z. So the z value is, it's an approximation because it actually turned those over here. It turned those fractions into decimals. Oh, that's why. Interesting. But it still looks like a horizontal tangent plane. It's pretty darn close. This is where your calculus would override, and you'd know that z is just f of 4/3, 2/3, and that would be the exact value. Okay, but I wanted to actually show you Wolfram Alpha instead, so let's go to Wolfram and show you that Wolfram can do critical points. So you can ask critical points of, let's see, what was our function again? X cubed minus 6x. So this is a good way also to check your calculus. It's going to be able to do both ways for the easy ones, but for the hard ones, definitely use a tech tool. Yeah, so there's our critical points, 4/3, 2/3, it's and x equals 4/3 and 2/3, that's the one we found, and -3/2 and -3/4. So again, our calculus checks with the calculator tech tool. All right, we'll stop there for this one.